So in the previous video we got the derivatives of the following trigonometric functions: y equals sine x, y equals cos x, and y equals tan of x. Now what I want to do is consider composite functions, composite trigonometric functions. Say something like y equals sine of 2x. Now we could go through differentiating this by first principles, work out f of x plus h and Newton's quotient and get the limit as h goes to 0 and so on. But I want to use the chain rule to calculate dy dx for this function. Not calculate, but get dy dx for this function. We're not actually plugging in numbers. We're just getting the derivative of a function. So what we do is we just let the chain rule, as you've seen before, I'm sure, is we let u equal 2x. So what we get if we do that is y equals sine of u. So now we have y as a function of u, and we know straight away that the derivative of this function, dy du, is just cos of u. Okay, so we just look up the derivative of sine in your tables, and you'll see that it's cos. You know, instead of x we have u. That's the only difference. So sine of 1u corresponds to sine of 1x. So its derivative is cos u, or cos x. So that's dy du. Of course, we don't want that. We want du dx. So what we do is we take this here and we calculate, well, we don't want du dx either. We actually want dy dx, but in order to get dy dx, we need du dx. Du dx is the derivative of this function u with respect to x, and that's just 2. And as I've explained before, if we want dy dx, we just multiply dy du by du dx. And these things actually behave like fractions. They're not actually fractions. It's more complicated, but they effectively behave. These terms cancel, just like cancelling above and below the line for ordinary fractions. So you see that we end up with just dy over dx, which is what we want. So we know that we have to multiply these together. So we have to multiply cos u by 2. Of course, this is not cos 2u, certainly not equal to that. And the argument of the cos function is just u. 2 is brought to the front. So we have 2 cos u, and we sub back in for u. U is 2x, 2 cos 2x. So now you can see what you need to do. So if you want to differentiate y equals sine of 2x, you just go to your tables, look up the derivative of sine. You see that it's cos. So you write down cos, and write down the angle as well if the angle is 2x. But then you multiply this thing here by the derivative of 2x. So let's look at another example. I won't use the chain rule. Suppose we have y equals cos of 5x. Then if we were to go through the chain rule, what we'd get is the same as just looking up cos x, which is minus sine x. The derivative of cos x is minus sine x, but our angle is 5x, and multiplying by the derivative of the angle, which is 5, and we bring that 5 to the front, so we have minus 5 sine 5x. So that's what you do. So I didn't use the chain rule here. You don't have to use it in the future. Let's look at another example. Let's look at y equals tan of, say, 9x. Then dy dx is got by looking up the derivative of the tan function, which is sec squared of x. X in this case, well, is 9x. But then by the chain rule, we multiply by the derivative of 9x, which is 9. So we get 9 sec squared 9x. Now what if we want to differentiate this function, y equals sine squared of x? Well, what we do is we let u equal, well, first of all, we must recognize that sine squared of x means sine of x all squared. By the way, the graph the graph of sine of x looks like this. But if we square this graph, squaring makes everything positive, we get something like this. But anyway, that's just an aside. So realizing that sine squared of x means this, what we do is, if we're going to use the chain rule, let u equal sine of x. So I'll have to go through this once by the chain rule, and then you'll see how to do it. Now, if u equals sine of x, that means that y equals u squared. So that means dy du equals 2u. Du dx, well, we'd have to differentiate this function here, sine of x. We just looked that up, we see that's cos x. So now we see that dy dx is got by multiplying dy du by du dx. Okay, the du's cancel as I explained before. So dy du is 2u, du dx is cos x. But what is u? U is just sine x. So we get 2 sine x times cos x. So that's the chain rule, but you don't have to go through all this chain rule business, of course. You just see the pattern. So if you want to differentiate y equals sine squared x, you deal with the power first, and then you deal with the function. So I'll just write it down again here. Y equals sine squared of x. So to get dy dx, you deal with the power. So you multiply down in front by the power. You get 2 sine x. Okay, well, you'd have a 1 here by default, but that 1 is normally not there, of course. It's just sine x. If it was sine cubed x, we'd have 3 sine squared x here. So that you deal with the power. And then that's the first thing. And then you differentiate the function. The function is sine of x. The derivative of sine of x is cos x. So you multiply this by cos of x. Let's take another example. Suppose we have y equals tan cubed of x. Now I'm not going to go through the chain rule. The chain rule leads to this approach. We deal with the power first and then the function. So to get dy dx, we just differentiate the power, if you like. Well, we're not differentiating the power, but it's like u to the power of 3. We're getting dy du, which is 3u squared, or 3 tan squared x. So that's the power dealt with. Then we go to the function. Now the function is just tan of x. Forget about the tan cubed of x, just look at tan of x. The derivative of tan of x is sec squared x. So we write down sec squared x, forgetting about the 3. So that's our answer, 3 tan squared x sec squared x. Now we can go further. Let's consider this function, y equals tan cubed of 2x squared. So we have an angle that's a composite function as well of x. Well, y involves a function of a function of a function, if you like. Now in another video I used the chain rule to explain how to differentiate this. So in that other video, I let u equal, or v equal 2x. So we'll have tan cubed of v, and then I let u equal tan of v, so that's equal to u cubed. So I end up with derivatives like dy dv times dv du times du dx, and the dv's cancel the du, so we're multiplying 3 derivatives. Now I go through that in detail in another video, so I won't do it here. I'll just apply the upshot of that, which is the power function angle rule. So we're extending now from power function rule to power function angle, because our angle is more involved. It's not just x, it's 2x squared here. So what we do is we take care of the power first, like before. Like before in the previous example, we have tan cubed, so we get 3 tan squared of our angle. We don't change that. Then we deal with the function. The function is tan, just like before. We look up the derivative of tan, we see it's sec squared. So we have sec squared of our angle, which we don't change, it's 2x squared. But now we go one more step and we differentiate the angle. So we differentiate 2x squared. That gives us 4x. And that 4x is brought to the front. It's not part of this argument, the argument of sec squared. 4x is brought to the front. So we have 4x times 3, which is 12x. So we have 12x times tan squared of 2x squared times sec squared of 2x squared. That's our final answer.